Okay, we're going to be going over Unit 4.6, approximating values with tangent lines. Okay, so remember, a tangent line in this form right here is a equation of a line tangent to a point. The point is here at x1 at y1, and then we have the slope. And I do want you to know that the slope is also a derivative. So the reason you use this, because sometimes you can't evaluate a function directly, so you have to approximate it using a point that's close to it. And tangent lines can help us with that. Okay, so first, let's practice writing the tangent line. We have a function right there. So the first thing is to find the point. It tells us that x equals 0. So basically we substitute 0 into our function to find the y component. Okay, so if we evaluate this, this is e to the 0, which is 1. All right, so this is 1, and then it's going to be times 3 plus 5, which gives us 8. So the point we're going to use is 0, 8. Now we just need to find the slope. The slope is with the derivative, so we do have to take the derivative of f. So if I take the derivative here, the 3 is a constant, so nothing happens. The derivative of e to the 2x is just e to the 2x. But by the chain rule, we do have to take the derivative of 2x, and that equals 2. And then we take a derivative of 5, which is a constant, so that's plus 0. So now that we have our derivative, we just have to substitute 0 into that. And if we evaluate this function, again, we have 0. So e to the 0 is 1 times 3 times 2. And that equals 6. So that is our slope of our tangent line. So let's substitute our values in for the slope. So it's y minus y1, which is 8 in this case. The slope is 6, and the x is 0. And so, yeah, so if we simplify this, we're going to get y equals 6x plus 8. And there we go. There's the equation of the tangent line. Moving on to example 2, it says the derivative of the function is given by the y equals k of t, and dy dt is equal to 1/4 times the quantity y plus 5. It is known that k of 3 is 19, so it gives us our point right there. Then it says write an equation of the tangent line when t equals 3. So this is your t value. This is your y value. So think of this as your x and y. We already have our derivative. So since we have our point, let's just figure out our derivative. And it's already given to us, so we just have to substitute the y value when t is equal to 3. We know when t is equal to 3, y is 19. So we just plug in 19 here to solve for the slope of the tangent line. So if we simplify this, we get 24 times 1/4, which equals 6. So again, yeah, we have our slope of 6 and a point of 319. So if we substitute in our values, y was 19, the slope was 6, and t, or the x coordinate in this case, was 3. And there's the equation. If we simplify it, we're going to get 6x minus 18, and then we're going to add the 19 to it. So we do get 6x plus 1. And we kind of explained this in the beginning. So why do we do tangent lines? Well, if we're like trying to approximate like 5.1, for example, with the curve, it's kind of hard to do if we don't have the equation. But if we can somehow find the tangent line, notice if we zoom in, 5.1 might be here. It might be like a minor error off of the actual value, but that's kind of the reason we do this. And you'll see some examples why. Example 3, we're given a table. It says that it's differentiable, which it has to be. And then it says let h of x equal the composition of f of g of x. And so we're trying to find the equation of the tangent line at x equals 4. So let's do some work up here. Let's plug in 4 to find the value. Okay, so g of 4, if we look, g of 4 is equal to 5. And then if we look at what f of 5 is, that's going to be -9. So we do have the coordinate for -9 as our point. We just have to find the derivative. So if we take the derivative here, we do have to do the chain rule. Remember, it's the derivative of this and then times the derivative of the inside. And so again, take the derivative of h, it's f of g of x, and then again times the derivative here for the chain rule. Sorry, I goofed up. I was supposed to put a derivative here. I missed that derivative. It's the derivative of f of g of x and then times the chain rule there. So I forgot to put the derivative here. So again, now let's plug in 4. So we already found g of 4. G of 4 is equal to 5. And g prime of 4 is going to be -2. Okay, so now f prime of 5 is going to be 3. And so we're going to have 3 times -2, which is -6. If I do the tangent line equation, it's minus y1. We have the slope, which is -6, x minus 4. If we clean this up, we get y plus 9 equals -6, x minus 4. And again, we could distribute the -6 through and then subtract the 9, but that's good enough. And then it says use the tangent line from part A to approximate 4.1. So all we're going to do is plug in 4.1 into this equation. So this is going to be 0.1 times -6. So this is going to be -0.6. And then if we subtract 9 from each side, we get that y equals -9.6. So that is an approximation of the value of 4.1. Okay, moving on to number 4. It says let y equals f of x be a function with this derivative and containing the point -1, -5. It says write the equation of the tangent line at x equals 1 and approximate 0.8. So we have a two-parter here. So we already have the point. We just need to find the slope, which is the derivative. We're given the derivative. So really all we need to do is plug in -1 and 5 here and here for x and y. Simplifying the top, I'm going to get 3. And the bottom is going to be -1 squared, which is 1. And so we get our slope is 3. And if we write the equation of our tangent line, we're going to use -5, 3, and 1. Which if we do simplify, that's going to be 3x minus 1 and then -5. So there's the first part. And again, that's because this turns into +5, and then you have to subtract it to each side to finish it. Now let's approximate 0.8 by substituting 0.8 into our function. So this is going to be -0.2. Subtract 5. So that's -0.6 minus 5. So this value is approximately -5.6. The last question on example 5, it says, on Thanksgiving, a delicious pumpkin pie is removed from the oven. Has a temperature of 175 degrees. The temperature of the pie at time t minutes can be modeled by the function p, where the derivative of p is that. Use the tangent line at t equals 0 to approximate the temperature of the pie 4 minutes after being removed from the oven. So notice that this function is the change in temperature of the pie given time. It only has a variable with p. So we do need this line to approximate because we don't actually know what the other variable is. We only have the temperature, right? So we do have to use this tangent line to approximate. So this one is slightly tricky because it's not giving you any information directly. Now we can deduce that at time equals 0, The pi is at 175 degrees. So let's write that. And that does give us our x and our y. Or in this case, our t and our y. You can think of it as x as well. And so the derivative at t is going to equal dp dt, which is equal to, so the derivative, so look at the rate right here, the slope of the line, we have to plug in the temperature here, and in that case it is 175 degrees at time 0, because that's what we're looking at. We're looking at time 0 initially, which is going to be 175 degrees because we're using time 0 to approximate. So the derivative at time 0 is going to be equal to negative 1 over 50 times 175 minus 25. Again, this is going to be 150 divided by 50, which is going to be 3. Oh, and it's negative. I almost forgot. So there is our slope. So we have our slope. We just need to figure out the rest of the equation. And we do have it, because we do have this value of 0 and 175. So our equation is going to be y equals, again, this is just negative 3x plus 175. Again, x minus 0 is x times negative 3. And then I just added 175 to each side to get there. And so now to finish our equation, it says we need to use this tangent line to approximate the temperature 4 minutes after it's in the oven, or out of the oven, sorry. So this is going to be negative 12 plus 175, which is 163 degrees Fahrenheit, because that is the temperature, or that's what it's measured in.